Fractions are part of a group of numbers called rational numbers. And rational numbers are the division of two integers. So for example, we might have -2 over +3. So remember, integers can be positive or negative. There's one exception in here. The denominator can't be 0, otherwise we're not going to get a number. Right? Dividing by 0 does not lead to a number. But 0 could be in the numerator. But just a note on this. -2 over 3 is the same number, in my opinion, as 2 over -3. Anytime you take a negative number divided by positive or a positive divided by negative, you get a negative answer. So those are 3 different ways to write the idea of -2/3. Consider it a negative number. You could consider it a negative number divided by a positive or a positive divided by a negative. Every whole number is a rational number because 3 is the same as 3 over 1, so it can be written as the division of two integers. 0 is a whole number because you can write it as 0 over 1. So take a second to think, can you think of any numbers that aren't fractions, that aren't rational numbers? Anybody? Does that mean every number that we know of is rational? How about 2.5? Would that be written as the division of two integers?
Over 1, yeah.
Okay, but if I write it over 1, the bottom is an integer, but the top is not. Okay, so that's not a proper rational number yet. But I could fix it. What could I do to this to get rid of the decimal? What's that?
2.
I could call it 2.5. Now it's a mixed number. And the trick for that is 2 times 2 is 4 plus 1 would be 5 halves. Yeah, so any decimal we write down can be rewritten as a fraction. And you could do it by reading it properly. So, and we'll go over this in the next chapter, but we say 2.5, but that's slang. The real way to say it is 2 5/10. Which kind of takes me back to this idea right here. That's going to give me 2 times 10 is 20 plus 5. This would be 25/10. So that's another version of that number. This right here, we learned a long time ago in math school that we can multiply top and bottom by the same number. So if I do that here, that shifts the decimal point. So there's another way to come up with the 25/10. So we'll get to this in the next chapter, but it turns out, although fractions are the majority of numbers in our existence that we experience, most of the numbers in the universe are not fractions. So then the question is, well, what the heck is a number if it's not a fraction? How do you deal with that? And we'll get into that. But so this is a fraction. This is a rational number. Numbers that are not rational, we'll talk about more later. You've seen it. Maybe a teacher mentioned they weren't rational. Pi is a number that cannot be written as a fraction of two whole numbers or two integers. And people have tried, they've never succeeded. It's been proven that it's impossible. It can't happen. Square root of 2 is another number that cannot be written as the fraction of two whole numbers or two integers. And there's a lot of numbers that are similar to pi in the square root of 2. Here's another weird example. Can you guess how I would continue that pattern? What would come next?
4 zeros.
4 zeros into 1, then 5 zeros into 1. It turns out if you continue that pattern, increasing the number of zeros by 1 each time and putting a 1 down, that cannot be written as a fraction. It's impossible. And again, next chapter we'll talk about why the heck that can't be a fraction. But it turns out there's a ton of numbers out there that aren't rational numbers, and they make up the majority of the numbers in the universe that exist, but our finite minds can only handle fractions easily. We can handle the other numbers, we just have to think really hard about it. It takes some getting used to. So this leads to some other facts about fractions. There's an idea called, I call it the fundamental rule of fractions. That if you have a fraction, let's call it a over b, and you take some integer besides 0 and you multiply it in the numerator and you multiply it in the denominator, then you've got a new version of that same number. So for example, 1/2, if I double top in the bottom, is the same as 2/4. Or if I tripled the top and bottom of the original, that would be the same as 3/6. Or maybe 10/20. So one thing that's kind of unique about fractions compared to whole numbers and integers is there's a ton of different ways you can write down the same number. Right? Think about that. Kids are used to, this is a chair. It's not a table, it's a chair. Right? Do we have many other words for chair? Not really. The number 1. Do we have any other names for the number 1? Not unless we jump into other languages. But all of a sudden fractions come up and we can call a fraction 1/2, or we can call it 2/4, and we can have it 3/6. That's a huge idea. We kind of take it for granted because we're used to it. But to kids, it's a big deal. It takes some getting used to. And that's something we can model. So my preference is to draw square cakes when I'm playing with fractions. And then I can cut that cake. And so here I'm trying to illustrate the idea of 1/2 by shading, say, this top half. But then just by recutting this cake, I can change it into other fractions. So for example, I can change it now into 2/4. Because by making that slice, I've made 2 pieces in the numerator, and I've made 1, 2, 3, 4 pieces for the whole. Remember, fraction is an equal part of a whole, equal parts of a whole. Now, on the other hand, I can this number n here, usually when we talk about that number n, we don't want it to be 0, and we start off with it being a whole number. But n could be a fraction, or we could use division. So we can tweak this rule a little bit. I'll do it with division. A over b is equal to a divided by n over b divided by n. I'll draw a picture of that. All right, so here is a picture of 2/6, to the best of my artistic ability today. And earlier we mentioned that division means groups in. So I can start looking for groups of 2 here. So here's a group of 2, and here's another group of 2, and here's another group of 2. So in this picture, what I'm showing is that starting with 2, 6, I can look for groups of 2 in the numerator, and I can look for groups of 2 in the whole picture. Should draw that in red. The red is where I'm looking for groups of 2. How many groups of 2 are in the yellow area? There's 1 group of 2. And how many groups of 2 are in the whole thing? There would be 3 of them. Right? So there's a dance. So division is regrouping things. Multiplication is kind of breaking things up again with fractions. So we can take fractions and we can grow them in either direction, but still have what we call equivalent fractions. So that's another term you'll see a lot, equivalent fractions. Oops. Equivalent. Now, equivalent fractions are equal, but I think the people that are newer to them, for example, 3/6 versus 10/20ths. So there's 2 ways to tell if 2 fractions are equivalent, at least. One way is to find a common denominator. Common denominator is that lowest common multiple that we talked about earlier. The other way we could do it is we could reduce the fractions. And generally to reduce, we want to find the greatest common divisor of the numerator and the denominator. And a third method is to just cross multiply. And my claim is that cross multiplication is just finding a common multiple, but not the lowest common multiple. So I'll demo each of these. So finding the LCM, we got to come up with what's the smallest number that both 6 and 20 go into. And we have a couple of different ways. We could start listing off multiples of 6 and listing off multiples of 20. Or we could find the prime factorization, which I'll do with you all. So 6 is 2 times 3. And 20 is 2 times 2 times 5, 4 times 5. So the LCM, the lowest common multiple, is going to have 2 times 3 in there. The next number says it needs another 2, and it needs a 5. And altogether, I'm pretty sure that gives me 60. And this is probably the hardest method of the 3. So then what would I have to multiply 6 by to get 60? 10. So we have to go up here, multiply top and bottom by 10. So then we're going to get 30 in the top here. What would I have to multiply by 20 to get 60? That would be 3. We multiply 3 by top and bottom there. And so I've turned each of these into 30 60ths. And so I can see they're the same number. So that's one method. Other method, 3/6 versus 10/20ths, would be to reduce them. And to reduce, we want to come up with the greatest common divisor. And there's a couple different ways you can do that. You could list all the divisors, you could use that Euclidean algorithm, or you can find the prime factorization. And we already have the prime factorization in these. 2 times 3, 2 times 2 times 5. So it makes sense to use that. So they only have a 2 in common, so that's got to be, oh, sorry, I'm doing this wrong. We also need the prime factorization of each numerator. So 10 is going to be 2 times 5. And 3 is just 3 times 1, or 3. And we have to consider each one individually. So here, the 3's divide out. So that's going to leave a 1 in the top and a 2 in the bottom. And here, a 2 divides out and the 5 divides out, leaving a 1 in the top and a 2 in the bottom. So using the GCD on each side, we can get them reduced down to the same fraction. So that's a little easier than the LCM. And then the last way to do it is probably the easiest way of all. 3/6 versus 10/20. Oops. Okay. And here we just cross multiply. So 3 times 20 is 60. 6 times 10 is also 60. So since those match, they're equal. Now, my claim earlier was doing this is essentially finding a common multiple for the denominators. Anybody have a guess at what common multiple I'm aiming for when I do this?
The LCM.
I'm not getting the lowest LCM, because when we found the LCM, it ended up making the denominators 30. Here, my denominators are 60. They're bigger than they were before. Now, I think the LCM is hard because it's a lot of work to get it. Then you got to find out which number to multiply by. Here, all I did is cross multiply. So question, what did I multiply this 3 by right here? 20. Now, to keep a fraction equivalent, don't I have to multiply the same thing to the bottom? Otherwise, I've made a new fraction, haven't I? What did I multiply the 10 by? 6. So what do I have to multiply by the bottom here? 6. Yeah, so it turns out, instead of going for the lowest common multiple, I went for a common multiple by just multiplying the existing denominators together. So I'm just saying, hey, 6 and 20 are right in front of me. I'm just going to multiply them together and say that's my new denominator. So I'm just saying 1/20ths are my new denominator. And it's really easy to get that because to get the numerators, I just have to cross multiply. And I can see they're both 60/20ths. So it's a way easier way to do it. That's why cross multiplying to compare fractions is so popular. You don't have to think about what is the best to reduce by. You don't have to think about what the lowest common multiple is. You just find a quick common multiple by multiplying the existing denominators together. And we'll come back to that idea later. But I think it's a pretty important one. Okay, so that's equivalent fractions. This idea of cross multiplying can also be used to compare fractions. So for example, what is bigger? Oops, it's a pen. Okay. 5/7 or 8/11. Now, some people are pretty good at just looking at that and saying, oh yeah, 5/7 is bigger. I'm not really sure. Anybody have a strong opinion one way or the other? Good. Cross multiply on this and see what happens. So if we try that technique, we're going to say take 11 times 5, that is 55. take 7 times 8, that is 56 on a good day. And when I did that, I just made 2 new fractions. Question, what's my new denominator? 9, yeah. When I multiplied the 11 by the 5, I'm secretly multiplying 11 by the bottom and creating a new fraction called 55/77. So this is hidden in the background. We're just ignoring that part. Over here, I multiplied 7 by 8, but technically I kind of got to multiply that into the bottom too. So I made 8 11s into a new fraction called 56/77. So it turns out 8 11s is a little bigger, but all I really care about is who has the bigger numerator, as long as I know they have the same denominator. So with the cross multiplication, we just believe they have the same denominator, and we just look at the numerators. Okay, so that's a nice technique for determining if 2 fractions are equivalent, or if one's bigger or less than another. So now I know that the inequality has to go that way. So I can say, oh yeah, 5/7 is a bit smaller than 8 11s. But they're pretty close on this scale, on the 77th scale. So if anyone looked at those originally and were like, man, I'm not sure which is smaller. They're pretty darn close. They're almost equal. Okay, one more fact and then we'll move on to addition. And this one just kind of blows my mind every time I think about it. And it's the idea of density of fractions. So technically 0 is a fraction and 1 is a fraction, right? And in between 0 and 1, like right in the middle, what fraction lives in the middle? 1/2. Are there other fractions that live in between? How many?
A lot.
A lot, yeah. We could make them up all day long. So, over here is 1/4, and somewhere between here is 1/3. Somewhere over here is 2/3. Over here is, let's say, 9/10. Way over here somewhere is 1/10. Somewhere close is 99 out of 100. And a little closer than that is 999 out of 1,000. And we could just, all day, we could just make up numbers, fractions that live in there. And here's the other crazy thing. If I were to zoom in on that part of the number line there, and put 1/2 here, so we just zoomed in there. Here's 2/3 over there. There's some number right in the middle, and there's a ton of others living all over the place inside there. So we could say there's infinitely many fractions between 0 and 1, right? But then if we pick any 2 of those, how many fractions live in between 1/2 and 2/3? Infinitely many. Then we pick 2 of those, like this guy right there and that guy right there, and we zoom in on them. So now we'll just call them fraction A and fraction B, and how many live in there? Infinitely many. What? How can there be so many infinities living inside of each other? It's this weird idea. But there are. And that's the idea. Fractions are very densely packed together, because between any pair of fractions, there's a whole bunch of other ones. And we can try and find them. So let's play a little game. I'm going to pick 2 numbers that are relatively close together to start with, but we're going to try to blow it up and look inside. So let's take, how about 5/7 and 6/7. We just zoomed in on 5/7 and 6/7. And we want to find a number inside. So just mess around for a minute. See if you can find a fraction or 2 that live in between 5/7 or 6/7. And then I'll go over a couple of ways, and you guys can tell me what you came up with. So here's a couple of things to think about. You could just average them, add them up, divide by 2. That'll find the fraction in the middle. So 11/14 is in the middle. And that was kind of a lot of work. Not a lot, but a little. Alternatively, I could just say, hey, that's the same thing as 500 over 700, isn't it? And 600 over 700. Now can you more easily come up with some fractions in between? Yeah, like 501 over 700. Or 599 over 700, right? Anything that's between 500 and 600, as long as 700 is the denominator. So if somebody told me they needed 100 numbers in between, I can easily find them. Anybody come up with some other tricks?
I like just times the denominator, so like I would go like 7 times 3. I would get 21, then I would do 5 times 3, and I'd get 15 over 21.
Yeah.
And then I could just like add to the top.
Yeah, so
number.
if we multiply both by 3, 15 over 21. Do the same thing over here, 18 over 21. So then somewhere in here is 16 over 21, and 17 over 21,
Yeah.
and 18 over 21. Yeah. Cool. Anybody else try something different? A couple of years ago, somebody showed me a really cute idea I'd never thought of. So they said, all right, right before 6 is like 5.9. They said, what about 5.97? And their neighbor said, well, 5.9 is not a whole number. They said, oh yeah, right. So call it 59 over 7. So it had to be a little less than 6/7, and they just had to assure themselves that it was bigger than 5/7, which then we could realize 5/7 is 50/70. So yeah, 59/70 is in between there. So with a little bit of work, we can find all kinds of different numbers that live in between, and those numbers are usually going to be fractions. Finding non-fractions in between is a little harder. Again, we'll work on that once we get to the decimal chapter. Okay, so next, finally, fraction addition. So we already did one example of fraction addition in activity 2. And there's 2 things I need to know to make this happen. So I want to model this. And a model means you need to have physical examples of what the numbers mean, and you have to have physical examples of what the operation means. So to do this, number 1, I need to know fractions are equal parts of a whole. And that addition means to combine and count. And so we'll look at a simple example with some cakes, and then we'll branch over to our pattern blocks. So let's just suppose we wanted to add 1/3 to 1/6. So I'm going to draw cake versions of each of these. So for 1/3, I'm going to cut vertically thirds and then shade one of them. Oops. So let's say there's no one here. And for 1/6, I'm going to do this a little bit different. I'm going to cut it horizontally in the 6. And whenever I have something like this, since it's even, what I'm going to do is cut it in half first. Oops, color. I'm going to notice I'm cutting horizontally there, so there's a method to my madness here. And then once I got it in half, then I can cut each of these in thirds, because 6 is 2 times 3. There's my best artistic attempt to make 1/6. And then I'm going to shade one of those also. And let's say this one right here. So I can't just combine them directly and say I have 2 pieces, because the pieces are different sizes. And that's a problem. That's like me putting a marker on the desk right here and saying there's 7 in the room. 7 what? people and markers. Right, it's kind of weird. So we have to get a common description. And one way to get a common description here is to cut each cake like the other. So I'm going to take the 6 cake and I'm going to cut it like in the vertical thirds. And I'm going to cut the thirds cake in the horizontal 6. There are other ways to do it, but I have something in mind for this particular way. So now this cake is 3 by 6, so there are 18 pieces in it. And this cake is also 3 by 6, so there are 18 pieces in it also. In the first one, since I cut that into 6 pieces, I have 6/18 in the 1/3 cake. And the other cake I cut into thirds after, so I have 1, 2, 3/18 there. So now that I cut each cake like the other, I can put them together and say I have 9/18. So now I'm doing my combining counts. Now there's this rule that a lot of teachers have, you should always reduce the answer. So let's think about reducing the answer. So I'm going to redraw this. So here's my cake. I'm going to put them all into one pan. I have thirds one direction. I have 6ths the other direction. I had 1, 2, 3, 4, 5, 6, and then I have to throw in another 1, 2, 3. So that's a picture of my answer. So a few different things you could do here. Somebody might look at this and say, well, I see groups of 3 living inside of your cake. How many groups of 3 are in the whole pan? 6 groups of 3 in the whole pan. And how many groups of 3 are shaded? 3 of them. And then that can be reduced further, right? How many groups of 3? Well, there's 3 groups of 3 there and 3 groups of 3 there. So I can see the whole cake could be broken down into 2 big groups. One of those big groups, if I take these 3 shaded ones and just transplant them, means I have one of those big groups, so I can break it down to 1/2. So by regrouping, we can just use the picture to kind of break it up again. So we can get it down to 1/2. So just a note about the way I did that. So mathematically, I started with 1/3 and 1/6. And I took the thirds cake and I cut it into 6. And I took the 6 cake and cut it into thirds. So I cut each cake like the other. So here, 1 times 6 is my numerator. 3 times 1 is my numerator. And I'm adding them. So altogether, I get 9 pieces out of 18. Because I have a common denominator for each. Have we done something like this before today?
With the shapes?
What's that?
With the shapes?
With the shapes or with the numbers?
What?
It's like the cross multiply.
Yeah, this is cross multiplying.
Oh.
Yeah, and we also did this shapes when we were working on activity 2, when we cut each of those pieces into the little triangle. So it's a similar idea. So here we have our 1/3 added to our 1/6. So a different version of adding fractions is to not, a common way to teach this is to find the lowest common denominator. But sometimes that's hard. An easier way to do this is just to say, hey, 1 times 6 is 6. 3 times 1 is 3. Your new denominator is 3 times 6. So the answer has to be 6 plus 3 over 18. And this is called the arrow method or the arrow algorithm for adding fractions. And later we'll compare this to the standard lowest common denominator algorithm and go for pros and cons on it. So we'll come back to that. All right, so we're going to take a look at our toys next. So here, this yellow hexagon is going to represent one hole. What would the green triangle be then? 1/6. And what would the trapezoid be? Yeah, so we could use these toys to say, if this is a hole, what would 1/6 plus 1/2 equal? And so then we can just take the toys and stick them inside of our figure and try and answer that question. Rotate that. Copy this into a new screen. So there's my answer. Oops, wrong button. I'm adding one of these. To one of these. So, oops, I guess I should have a yellow one in here too. So a key is important when you're doing this with kids to keep track of what a hole is. So up here I should make a note that this is one hole. And so here I have 1/6 plus 1/2. So to us, we're pretty good at this because we've done a lot of fraction stuff, but to kids, they're going to have to work a little harder. So what would you suggest we do to the red trapezoid? Split it with the triangles. Okay, so then take some triangles and build on top of, say, the red trapezoid. So I'm going to do that over here in my game land. There we go. Yeah, so here I'm just rewriting that as 3/6. But now it makes it easier for me to combine and count because I have the same type of thing. And so I can say, oh yeah, the answer is 4/6. Now, think about this for a minute. Is there possibly a smaller denominator we can work with besides 6? What's that? Well, the problem with the rhombus is a whole rhombus doesn't fit in here, and a whole rhombus is too big for this right here. So would you agree 6 really is the smallest denominator I can come up with? Yeah, I can't get any smaller than that. However, does the answer reduce? Yeah, it still reduces. So are any of you looking back at this example right here and thinking, man, 18, that seems like way too big for the denominator. Why not just use 6? So again, you guys are biased by past experience. You immediately see 6 is the common denominator. When young kids are first looking at this, some of the kids will see that 3 goes into 6, but others won't catch it right away. Okay. Do we want them to catch it? Yeah, we do. But how many people do you think fractions bring to tears? Many? Okay. So guess what the biggest problem with math and frustration is? Actually, no, it's
Oh.
parents.
Uh,
Yeah, they did some research. So yeah, people get frustrated with fractions. Signed numbers drive people nuts, and even decimals sometimes. But it turns out the biggest thing that led to people having frustration with math or fear of math is their parents. Why? Because they bring something home and the parents try to help and the parents get frustrated because they can't quite remember. And the kids think, oh, I got to get frustrated too here. Right? It's this learned anxiety. But if we give people other ways to look at it, then maybe it's not going to be so bad. Like not worrying about finding the lowest common denominator. It's a lot of stress. Let's just find some denominator. Don't worry about it so much. All right, back here. So here's the deal though, even if you do find the lowest common denominator, and 6 is the lowest common denominator, it's the lowest common multiple of 2 and 6, it still has to be reduced after, right? So what was the point of doing all that work? And now here it wasn't much work, but sometimes it is, because then I still have to reduce this down to what? 2/3. So, and this goes to what Ashley was saying. She said, well, what if we threw the blue rhombus in here instead? So I'm just going to do that next. So if I take the blue rhombus and I put it, let's see, I got to do it just right. Let's twist you a bit. And put, let's see, you need to be twisted a bit. There we go. 2 blue rhombuses make the same thing. So here I can see the answer is 2 out of a possible 3 in the whole. So these toys can be used to show how to add, and they can be used to show how to reduce, which is kind of fun. And you can play with them, hold on to them. Highly recommend physical toys than digital toys, because the whole mouse interaction and other technological problems, real toys are, I think, way better. Okay, so we're getting warmed up to activity 7. So if you could take a look at that. We just did example problem number 1 here. So the recommendation, so again, they're telling us at the top that 1 yellow hexagon is a whole. If that's the case, a red trapezoid would be a half, a rhombus would be a third, and a green triangle would be 1/6. And given a combination of shapes, like a red and a blue, they can be used to model 1/2 and 1/3, or a blue and a green, 1/3 and 1/6. Or we could do subtraction. Take a red, starting with a red, take away a blue. What's left? The intermediate step here is to rewrite each of those as greens and the associated fraction. So each of the problems down below is going to end up being rewritten like this. Let's see. Oh, they did 3 green, I see. Yeah, what we're going to do down here is, given the combination of shapes, we're going to rewrite it as some number of greens, write the related fractions, and then come up with a final answer. Sometimes the answer will reduce. So they gave us an extra line for reducing here. So start on those. The next page I want you to work on for homework. This one's going to get a bit more excited because now we have a new whole. So now we're going to say 2 of these things is a whole. And now a half is a whole hexagon, a 4th is a red trapezoid, a 6th is a blue rhombus, and now the green triangle is 1/12. Some things that can be used to help with this. I'd recommend taking home some of these toys with you. The other thing I would recommend is what's called hex paper. And so while you guys work on the first few problems, I'm going to print some hex paper out for you to take home with you. So why don't you get started on page 1, and we'll regroup in a few minutes.
So on the top line of those, they just want like how many greens?
How many greens? Yeah. Yeah, the top line is greens, the bottom line is fractions. There we go. All right, can you pause whichever one you want, but you're flying along there. So I just want to show you an example of one on the next page and how you can document some of your work for the next page. And this will come in handy in a couple of future ones. So I printed out what's called isometric dot paper. So the dots are all the same space apart on there. And the nice thing about that is it's easy to draw a hexagon. It's easy to draw that trapezoid. It's easy to draw the triangle or the rhombus. So what I want to do is, so this problem right here is the first one on the second page, 1/2 plus 3/12. So on the second page, they say 2 trapezoids as a whole. And then I want to use these toys to illustrate 1/2 and 3/12. Now we can totally take the toys in front of us and do that, but I want you to also get used to trying to draw this on paper too. So then I drew out my 1/2 as 1 hexagon, because that's half of the whole. And then 3/12 I initially drew as 3 triangles stuck together inside there. Okay. And then I want to combine them and put them together. So I combined them and put them together down here. And at first glance, if I think of breaking up the half into little triangles, I have 6 of them, plus the 3 over there gives me a total of 90/12. So there's one possible answer. But then as I looked at the way I had set them in there, I noticed that I threw them in and they happened to be 3 trapezoids. A trapezoid is what part of the whole here?
4.
It's a 4th, so I have 3 of those 4ths. Okay, so we want to try and reduce whatever possible. So then minimally, you'll have a couple of sketches for each problem, and you can kind of fit them in a little bit of space left on there, but you might want to redraw them on another sheet of paper. So when I did mine, I have a whole bunch of dot paper that I drew all over to illustrate some of these pictures. Okay? So if you feel it's too cramped to draw on page 2 of this, then definitely feel free to use that dot paper I gave you to draw these sequences out to try and come up with the sums and how to reduce them. If you need more dot paper between now and Wednesday, on the resources page, I have a link to my isometric dot paper link. So you can click there. That'll take you to a place where you can kind of design your own dot paper. The default is good. You could just go to download PDF and it'll download a file like the one I printed out for you. Another version of that is hexagonal paper, where it's already connected for you. So it's just a bunch of hexagons on the page. And some people like that better than the dots. So you pick whichever kind of paper you want. Use the stuff I gave you. I can print more, or you can go print your own online. So do what you can for homework in Activity 7. We'll talk more about addition and subtraction next class, and maybe we'll have time to move on to multiplication and division, but I'm not sure yet.